Alright, welcome to the NUPOC Video Study Guide number 43. Let's look at question 4 in the Calculus section of Guide 1. And this is asking us to just talk a little bit about how an integral is related to the graph of a function. Right? So intuitively, I think we all understand, right, the integral, if we're looking at the graph of a one-dimensional function, right? Let's have some sort of example, right? Let's look at something like this, right? This is our 1D function, this is x, and this is f of x, right? Now the integral is going to, the definite integral is going to give us the area, say, under the curve, between the curve and this axis, right? If we evaluate, if we have this definite integral. Now if we have just the indefinite integral, that will give us the function for which this, our function here, is the derivative, right? But it's also giving us the function that tells us sort of what the area will be under the curve, right, at all these different points, right? So we can then evaluate that from, between two different points and get what the total area is, right? And if we think about it this way, this is sort of a high-level view of it, right? But if we think about it, right, the integral is telling us, this is telling us sum, right, or summation, the values of f of x, right? So the integral of f of x dx, right, is telling us to sum values of the function, okay, so values of our function times some infinitely small dimension of the independent variable. It's a lot of abbreviations there, right? So what we're doing is, I'll draw another graph over here, right? Say we do something like this, right? And we're going from this point to this point. And let's say this is x equals a, and this is x equals b, right? And we want to integrate, let's say, from a to b. What we're doing, right, is we are taking the value of the function at a certain x times an infinitely small dimension of the independent variable x, and we're doing that lots of times because this is infinitely small, so we're taking an infinite number of these small slices of the function and then summing them up, right? That's what the integral is. It's like this big script s, right? So we take the value of the function, multiply it times some infinitely small area, we get this rectangle, and then we do it again as we go towards b, right? So we're doing all of these, and we're summing them up. And that's how you would get the area under the curve, right? If I summed up all these rectangles and they were infinitely small, I would get the area under this curve, etc. Right? And so you can think about it this way, right? The integral, and we will actually, this is another way to write it. There's actually a couple ways to write it, but the integral of f of x dx, let's say from a to b, right, is actually saying, let's actually do a summation, right? So it's saying let's do a summation from, let's have some variable x, right? So from x equals a to x equals b, our function x times some delta x, and then take the limit as delta x goes to 0, right? So we'll show this, there's a couple other ways to write it. One where we have a variable n. Here delta x is the width of each rectangle. Another way to write this is by instead letting delta x sort of vary and doing it in terms of the number of rectangles between 2 points and letting that number go to infinity, right? That's another way of writing it, but we'll show this. I think it's in a couple problems where we actually define integration. In fact, it might even be the next problem. Let me peek over here at the study guide. Right. Yeah, I think it is. It is the next problem. So in the next video, we'll probably go ahead and develop this. But anyway, so this is exactly what I just said we're doing. We're taking the value of the function, multiplying it by some infinitely small dimension of the independent variable, and we just sum all those up. And so that's why it represents the area under the curve. And of course, if we got a two-dimensional surface, right? The integral will give us, say, the volume enclosed between that surface and, say, the xz plane or something, right? And so it'll be one dimension higher than the actual curve that we're integrating. So yeah, it's an interesting way to think about it, and we'll go ahead and develop this in a future video.